You let us know when we're podcasting.
Yes, we are broadcasting right now and recording.
Okay, perfect. So welcome everyone to the session 5B on network analysis and optimization. We have on schedule 6 talks. We have already 5 of the speakers here. Hopefully we'll get the last one joining us in the middle of the presentation. Each one is going to have 6 minutes for their talk. I'm going to let them know when they have only 1 minute remaining. The first speaker is Rattanaporn, Kaewkluengklom. It's a joint work with Fumitaka, Kurauchi, Toshiyuki, Nakamura, and Takenori, Iwamoto from Gifu University and Nagoya University and the Shizuoka Railway Company. Please go ahead, Rattanaporn.
Yes, sure, thank you.
You please can share your screen.
Yes, thank you so much. Good morning, sorry?
Yes. Put it in full mode so that we can, presentation mode.
Yes.
Perfect. Go ahead.
And good morning, everyone, and I hope you guys see my slides already. First of all, let me introduce myself first. I am Rattanaporn, the PhD student from Gifu University, Japan. Today, I would like to talk about my research in the topic of applying the hyperpath concept to evaluate the accessibility of public transit network. Let's start from the motivation. In many cities with high service operation, it leads to a common bus line problem and hyperpath route choice principle, where passenger is generally assumed to reduce their expected travel time by considering the set of alternative line. Additionally, in order to increase the understanding of topological characteristics, this study also do consider the network analysis concept, considering its level of service to evaluate the accessibility based on generalized travel cost. It is interesting that developing approach when particularly the attribute of transit service are differences of interest. Therefore, the objective of this study aims at first indication the concept of choice complexity to compute the expected travel time as the new type of weight to evaluate the accessibility, and then we compare the results of accessibility with the previous study approach to confirm our method. Regarding the methodology, this study conducts the combination of bus and rail network from Shizuoka, Japan by using 2 databases, including smart card data and public network service. We first generate the graph of public transport network from database for original public transport network, or is so-called L-space network, and space of service or P-space topology. We then extract the travel time from AFC data because we don't have such kind of GTFS data available in this study area, and then we calculate it into unweighted P-space network. From this graph, this study also to consider about walking path within 500 meters to connect among the bus stop and the railway station. We also do we assume the regular arrival in the method. Regarding the third step is computing the new travel time as a new type of weight and assigning into piece-based network. This step shows how difference between our method and the previous study method. The different thing is that our study method proposed the optimum hyperpath algorithm to search for the minimum value between OD pair, whereas previous study consider all possible service surfing along OD pair. And for generalized travel cost in this study is comprised from in-vehicle time, waiting time, and time transfer penalty cost. We finally searching for the minimum travel time for each origin to the destination by Dijkstra algorithm. And next, I'm going to move to the results of this study in comparison of accessibility between 2 methods. As shown in this figure, this shows the shorter travel time or high accessibility, or is shown in the light yellow, in the center city and nearby railway station. By the results of previous study also show quite similar with our method. Moreover, the distribution of generalized travel cost and the comparison of time gap between two methods also show even both methods are quite similar results, but considering hyperpath approach can minimize the time of OD pair, which is more realistic for expect travel time. Finally, in conclusion and future study, this study can summarize that the optimum hyperpath approach can minimize the total time, which is more realistic for passengers who do not rely on the timetable to expect the travel time at stop. And we can also summarize the factor affecting accessibility that are from the frequency of bus service, the bus stops having longer distance, the bus stop have many number of transfer, and so on. However, for future study, since existing public transport in this state is not significantly reliable, so we will extend to more comprehensive network in the further study. And we also interested to examine bus route choice probability to answer the question whether or not passengers really enjoy the hyperpath set. Yes. Therefore, to more information, please see my longer presentation, and please feel free to drop me any question. That's all for today. Thank you so much.
Thank you, Rattanaporn, very much. Next speaker is going to be Igor Dakic. Please go ahead, Igor.
Yes,
Igor,
let me just share my screen.
Automated modular bus system, a macroscopic perspective. This is a joint work with Kaidi and Monica Menendez from ATH and Stanford and the New York University at Abu Dhabi. Go ahead, Igor.
Thank you. So as you could hear, my name is Igor Dakic. I'm a PhD student at ETH Zurich, and Kaidi is a former colleague of mine. He's now a postdoc at Stanford, and Monica Menendez is my supervisor. She's currently at NYU Abu Dhabi. So in this work, we are trying to introduce the automated modular bus units for the purpose of improving the performance of the bus system, and we aim to do that from a macroscopic perspective. Now, why the modular bus units? Here we have an example of a bus, which is probably the smallest size that we can send. Let's say like during the night when we have a low passenger demand, and we can see that in that case, we have underutilization of the vehicle capacity. So we have like 1, 2, maybe people inside. So very low passenger occupancy, but high operating cost. And the idea with the proposed approach is essentially instead of sending a bus with a relatively higher passenger capacity in case of low passenger demand, we would like to send a group of few combined modular bus units, which are also fully automated, which means they're not cost for assigning drivers to them, which overall have lower occupancy, lower capacity compared to a regular bus, which kind of like leads to the increase in passenger occupancy, but at the same time, it has lower operator cost. So this provides enormous flexibility for an operator to basically better manage the allocation of the vehicle resources and reduce its cost. Now, unfortunately, I do not have time to go in details with what is the methodology behind, but it's important to note that in this work, we're actually the first who accounts for the interactions between bus mode and private cars. And instead of just like improving the performance of the bus system, we essentially trying to improve the performance of both modes, basically for the entire network. And here we have the results. So basically we have the improvement in the total system cost, and also we have the improvement in the total operator cost. We have different scenarios. Each scenario characterizes what is the car demand and what is the bus passenger demand. So for instance, LH means low car demand and high bus passenger demand. And we have different penetration rates of modular units, which means basically, okay, so one conventional bus is considered as one conventional unit because it cannot be combined like in railway system. So we have like a single bus, and then modular buses are those fully automated and they can be combined. And we have like 10, 20, 30, or 40% of these modular buses in the entire vehicle fleet. We can see that as we are increasing the penetration rate of modular bus units, we are essentially achieving higher improvements in the total system cost, as well as in the total operator cost, which in case of the total system cost can be even about 15%. And in case of operator cost, it can be almost as close to 75%. The biggest improvement is exactly in case of low car demand and low passenger demand, what we essentially said at the beginning. Basically, instead of sending more buses which are combined or high bus capacity when we don't have like enough demand, we just send basically a group of few combined modular bus units. And we can essentially see that from this graph, which shows what is the average number of combined modular bus units. So you can see that basically we are sending like a single or two combined modular buses when the passenger demand is low. And then as the demand for both modes increases, we essentially increase the number of units combined, which at some case can actually go also to 6, which is basically the threshold that we put. So approximately 6 modular bus corresponds to one articulated bus. And the reason for this is that because we are accounting for the effects of traffic conditions, if we have more buses driving around, basically they stop more often and they produce like in mixed lane bigger effects on car traffic. So that's why we can actually see that for low passenger demand, we essentially send just like few combined units. So to wrap things up, in this work, we propose new flexible bus dispatching system, which contains modular bus units and conventional bus units. In comparison to the existing bus dispatching system, we achieve much better performance. We jointly optimize the allocation of the vehicle resources, both conventional and modular bus units. We also optimize basically what is the number of units combined, and we also optimize the dispatch frequency. And we additionally show the value of considering mode interaction. It's done by comparing what should be the result if we only consider the bus system without accounting for the effects on traffic, and what is the performance of the system when we actually take into account the impact on the traffic performance. And we can see that it's really important to account for the effects of traffic, because by accounting for traffic, we essentially get like much higher improvements in the total system cost. So thank you for your time. I hope
Thank you, Igor. Right on time.
Thank you very much.
Please go ahead and put your questions in the union. There's a Q&A spreadsheet in which you can ask to different speakers. Please go ahead and start putting your questions there or in the chat as well. Then our next speaker is Nurit Oliker. She'll be presenting a frequency-based transit assignment model that considers online information. She's from the Université of Montréal. Go ahead, Nurit. You can put it in the presentation mode.
Yeah. Okay.
Perfect. Go ahead.
Okay. So, hi, good morning. So my name is Nurit Oliker. I'm currently a postdoc fellow at the University of Montreal, but I'll present a part of my PhD conducted at the Technion in Israel. And in the scope of planning models, so this is a frequency-based transit assignment model that considers online information. So our main motivation when we started was that commonly used models for planning assume passenger aboard the first arriving vehicle among some set of attractive lines. And nowadays we have more and more technologies that inform the passenger of predicted arrival times. And this information is likely to influence path choice. For example, one may choose to skip an arriving vehicle if a better one is predicted to arrive soon, or alternatively board a slower line in case a faster line is delayed. So our objective was to model these kind of behaviors within a rather traditional framework of frequency-based transit assignment. So we considered in the modeling, we considered two types of available information. We had the partial info where passenger received predicted arrival time at the boarding stop only. And we had the full info where the passenger received predicted arrival times at both the boarding stops and their following transfer stops. So in the second case, they have the full prediction of their waiting times along their path. So we treated each of these cases separately. This is the general scheme of the model. The inputs are the transit network and the demand metrics. The first step is to form the hypernetwork, where the graph consists of explicit arcs for each line segment. Then for each OD pair, we first find a set of attractive routes, meaning any route that under different condition of arrival times can be the optimal. Then we define the decision rules for selecting these paths. For example, if line 1 precedes line 2 in more than 5 minutes, board line 1, etc. Then we calculated the probability for these cases. This was the more complex part of the work. We developed some analytic equation and also applied convolution. And finally, we assigned the demand accordingly. So some results for the benchmark network of Winnipeg. So here we compare the classic optimal strategy model from the AMI to, we applied it, but it's the original model of the AMI. And we compared it to the partial info and full info cases I presented. So as could be expected, as more information, the passenger can exploit it to reduce their total travel time. But what was more interesting, we received a very different distribution of passenger in the network. For example, passengers tend to do less transfers in the partial info, where they have only the information at the boarding stop, so they choose more direct path. But if they have the predicted waiting times at their transfer stops, they can use it to do more transfers with the relatively low cost. So to conclude, this study demonstrated potential impact of available information on route choice and assignment results, and emphasized the importance of its consideration in planning models. Generally, the more information available, path sets were wider and enable higher flexibility to the passengers. Passenger could better exploit the transit network and enjoy reduced travel times. Please feel very free to contact me for any question or comment. Thank you.
Thank you, Nurit. Very good in the timing as well. And please go ahead with the questions in the Q&A from the union. There's a link to the spreadsheet in which we are collecting questions for each of the speakers. Our next speaker is going to be Leah Ricardo. Public transportation reliability, learning long-term travel time density to measure reliability and move towards reliable schedules. This is a joint work with Guy de Saulnier, Andrea Lodi, and Louis-Martin Rousseau from the Université de Montréal and the Polytechnique Montréal. Go ahead, Ricardo.
Okay, can you see my screen?
Yeah, we can hear you now. Perfect.
Okay. Wonderful. Okay, hello everyone. Today I will discuss the work done in partnership with Gifu on public transportation reliability. In the last couple of years, reliability has gained attention in the field of public transportation. In some cases, it was found that passengers put more value on the reduction of travel time variability than over the reduction of travel time itself. Some instruments to control the travel time variability, as vehicle holding, priority at traffic light, and exclusive lanes, have been successfully applied. Nevertheless, day-to-day disruptions and variability are considered unavoidable on the day of operation. So we ask ourselves, knowing that the travel time is impossible to completely eradicate, how can it be addressed at the tactical level to reduce chances of unreliability during operation? So we propose a new approach considering the stochasticity of travel time when solving the vehicle scheduling problem, the VSP. Okay, the reliability of a bus schedule is assessed by its daily tolerance. In the figure here, we have an example of daily propagation. The light orange strips represent the planned travel time, and the dark orange strip represent the travel time deviation. In this example, only trip 1 has a travel time deviation that propagates to consecutive trips, because the buffer time between trip 1 and 2 and between trip 2 and 3 does not allow full recovery. We call also this type of delay secondary delay. We have them here and here. Let me take this. Okay. So what we want to measure, actually, to measure the reliability, is the probability density function associated with the random variable of the secondary delay duration that we denote capital R. By looking at the equation and without going too much into the details, we can see that the secondary delay is recursively computed using the travel time density that we denote capital TT. So in the next few slides, I will explain how we predicted the density of the travel time using AVL data. So in the planning process, the vehicle scheduling problem is solved a few weeks in advance. Hence, the prediction must be done one step ahead. As far as we are close to the end of planning period T, the operator is already planning the schedule of planning period T+1. The learning task we carried out consists of computing before the end of period T the estimate of the true density of the travel time of period T+1. Here in the figure, we have two examples of such estimators. To train the estimator, we only use the historical data, the training set. And in this example, when we compare the estimators to the histogram of period T+1, that is the test set, we see that the estimator 2 is overfitting the training data, while estimator 1 generalized better to the new period. So in this case, we would prefer estimator 1 over estimator 2. The data set we used was collected during a 2-month period in the city of Montreal. The 50 routes with the highest number of recorded trips were kept. So we had about 41,000 trips recorded. The long-term travel time density must be based upon features that are available a few weeks in advance, again, since it is a one-step ahead prediction. So for example, the meteorological conditions, which are likely to influence the travel time duration, are not considered, since it is not a value that is known for sure a few weeks in advance. Based upon a feature analysis, we selected for the feature set the line, the direction, the scheduled departure time, and also the week number. We compared different models, including parametric unimodal statistical distribution in the graph going from the Kurauchi to the log logistic distributions. And also we tested conditional kernel density estimation, the KDE, and the smoothed log logistic regression for probabilistic classification, the LRPC. Most of the models, except the LRPC, are conditional, meaning that they are trained based upon the travel time of similar trips in the training set. The performance is evaluated by the NLPP, which is the negative log predictive probability on the test set. By looking at the graph, we can see that the 3 last models yield the best results. The previous result will be used to improve the reliability of vehicle scheduling problem by implementing a B-objective vehicle scheduling problem.
1 more minute, please.
Yeah, the preliminary results on real-life instances are promising and show that considering travel time densities, we can reduce chances of delay propagation with little loss of cost efficiency from about 0.1 to 0.2% of loss, and by using the same number of vehicles. So that's it for me. If you have any question or want to chat about it, please feel free to contact me or ask them in the Q&As. Thank you.
Thank you, Leah. Our next speaker is going to be Sara Ansaliadei. She will be presenting a stochastic transfer synchronization in transit network, comparisons of alternative formulation. This is a joint work with Mert Bodur and Amer Chalabi from the University of Toronto. Go ahead, Sara, please. You're muted. Sara?
Hello, everyone.
Go ahead.
In this short presentation, I want to talk about, can you hear me?
Yes, now I can hear you. Go ahead.
Oh. Can you hear me?
Now we can hear you. Go ahead.
So you can hear me, yeah?
Yes.
So this short presentation, I want to talk about how to formulate stochasticity in transfer synchronization and how crucial is to have a detailed data. Transfer nodes provide commuters accessibility to transfer nodes provide commuters
I think we lost our speaker. We will wait to see if she can rejoin us. And in the meantime,
I just
got
connected.
You're back. Go ahead, Sara.
Sorry for that.
Yeah.
Transfer nodes provide commuters access to an efficient connection amongst pairs of origin destinations choices. However, without well-synchronized routes, the disutility of transfers may taint the system noticeably. Also, due to the inherent stochastic nature of transit systems and high penalty of missing a connecting bus, special efforts need to be dedicated to provide smooth transferring. Individually without synchronization among intersecting routes, but also the stochastic nature of transit system is not well treated. So the focus of this study is at the scheduling stage with the goal of developing synchronized timetables at the network level while considering the uncertainty in bus running time. So
There's a problem with the connection from Sara, so we'll see if she can reconnect again. Otherwise, we are going to give the time to Alireza so that in the meantime, Sara can reconnect and probably later finish her talk. So I'm going to introduce then our last speaker, who's Alireza Kani. from the University of Minnesota Twin Cities. He will be presenting his work on transit origin destination estimation for special events, a compression sensing approach. This is a joint work with Pramesh Kumar. Go ahead, Alireza.
Thank you, Ricardo. Can you hear me okay?
Yes, we can hear you perfectly.
Okay, great. Thank you. Good morning or good time, everyone, depending on where you are in the universe. I'm going to talk about a special event demand or ridership estimation method. Depending on the settings, it can be an origin destination estimation, ridership estimation, etc. But the estimation technique is what I'm going to introduce here with some applications. So special events are defined to be the occurrences that abnormally increase the demand, the traffic demand, transit demand, etc., as opposed to incidents that reduce the capacity. So anytime there is an imbalance in demand and capacity because of increased demand, we call it a special event. They can range from very large, tournaments like Olympics, etc., or to small local events. The picture I'm showing here is the Minnesota State Fair, a 10-day event, the largest fair in the United States with about 2 million participants in 10 days. So there is a lot of additional or demand to the State Fair ground. Transportation agencies, including Metro Transit, provide different transportation options. Some shuttle buses, some new parking spaces, etc. But still there is a high stress to the transportation network because of this additional demand. So specifically about transit, we wanted to know if there is any method to detect these special events and to quantify the additional demand because of the special events and the performance of the transit system. Unfortunately, we didn't find anything in the literature in terms of a mathematical framework to quantify this extra demand. So the objective is to come up with a method, a robust method, to detect the special events from time series data and to quantify the extra demand generated during these events. So this figure here shows the 3 bus routes that serve the Minnesota State Fairground. The upper route is a BRT line, the other 2 are a local bus route. And as we see the highlighted area, about 10 days of the duration of the State Fair, we have slightly larger demand. It's not quite visible here, but we can see that actually this is a significant increase in the transit ridership for these 3 routes, and it can affect the performance of the routes. So we take this data, the time series data, and first of all, we reformat it in a very big matrix. We call it matrix M. Each row of the matrix represents one origin destination, or depending on the problem setting, it can be the boarding at one particular stop or alighting at one particular stop. The columns of the matrix represent the time intervals, and it can be, for example, hourly time interval within a month, so that would be 24 hour times 30 days, for example, or it can be morning peak, midday, afternoon peak, again for many, many days. This is going to be a huge metric. Now, we assume that, well, actually, we know that the passenger flow follows a periodic trend. For example, the demand that we observe every Monday morning is going to be pretty much the same. The demand on Wednesday night is going to be pretty much the same, and weekend will be different, etc. We assume that this high dimensional demand matrix M lies in an approximately low dimensional subspace. So the goal is to recover this low subspace of matrix M and decompose M into a low rank matrix and a sparse matrix. Initially we used the principal component analysis, PCA, to recover the low dimensional subspace of matrix M and the sparse matrix of a special event demand. However, there are issues with the PCA. It's hard to solve it for large networks, for large instances, and it's very sensitive to noise in the data. So we modified this to a stable principal component pursuit, SPCP, to overcome these computational and sensitivity challenges. So the formulation looks like this. We are given matrix M, and we are going to estimate matrices L and S. We minimize the nuclear norm of matrix L, which is the tightest convex relaxation of the rank of matrix L. And we also minimize the L1 norm of matrix S as the tightest convex relaxation of L0 norm that represents the sparsity of the matrix. And in the constraints, we want to constrain the difference between the observed matrix M and the estimated matrices L and S. So despite the simple look of this metric, it's very difficult to solve in large instances. And I'm not going to talk about the solution algorithm, but I refer the audiences to the paper that is just published in IEEE Transaction on ITS. So, and I'm happy to answer any question about the solution algorithms. Application to the Minnesota State Fair event. Again, this is just for the A9 BRT, which is the high ridership route covering or serving the state fairground. The top figure shows the observed ridership on different days, and we are seeing 5 weekdays with high demand and weekends with a slightly less demand. And suddenly we have these jumps. Note that this is not daily, this is per, I believe, 3-hour intervals. So we have a few points showing the daily demand and the small lower points that show the demand during the night times, which is much less than that. We decompose this matrix M to matrix L that shows a periodic pattern of the demand, and we can attribute this amount of demand to the regular users of the route. And also we estimated matrix S, which shows the high additional demand during the state fair event. So we can quantify how many more passengers are using A9 BRT just because of the special event. This figure shows it from another perspective. In each figure, the horizontal axis shows the stations along the route, and the vertical axis shows the days. We have about 30 days. And if we notice...
1 minute.
Sorry, 1 more minute?
Yeah, go ahead.
Okay. So again, matrix M, L, and S, and we can see that the matrix S, the special event demand, is nicely recovered during these 10 days and at some particular stops. So this column that has these dots is the station closest to the state fairground, and we have the highest alighting at this point. In order to compare it with an alternative method, we simply subtracted the amount of observed demand or the average demand from the observed demand to see whether we can just simply subtract the demand and get the regular and special event demand. This last figure shows that, which is very sensitive to the noise, and it's hard to detect where and when the additional demand is happening. But, last slide. On the right, I'm showing the additional demand or additional load on the bus route and how we can detect where along the route we need additional services. So instead of increasing the frequency for the entire route, we actually need to increase the frequency in just one section of the route to serve the additional demand. So in summary, we proposed a mathematical framework to detect the special event ridership or demand for transit systems. An application to full network would be very interesting, but not without challenges because of the large matrix M. And also application to service design for basic riders during the pandemic when the demand is much more sparse is an interesting topic that we are currently working on now. And then I'd like to acknowledge Pramesh Kumar and my students, also the sponsors, and Metro Transit who shared the data with us.
Thank you very much, Alireza. And we're going to try to have a second chance for Sarah, who had a lot of problem with her connection during the first time. Hopefully now it's more stable. And so Sarah, if you can share your screen and start your presentation again, I guess, please.
From the beginning?
Yeah, maybe it's better to remember everyone what we were talking about. Thank you very much. Go ahead.
Sorry again for before. Transfer nodes provide commuters access to an efficient connection among pairs of origin destination choices. However, without well-synchronized routes, this utility of transfers may taint the system noticeably. Due to the inherent stochastic nature of transit system and high penalty of missing a connecting bus, special efforts need to be dedicated to provide a smooth transferring. That being said, in practice, not only are bus timetables generated individually without synchronization among routes, but also the stochastic nature of transit system is not well treated. So the focus of this study is at the scheduling stage with the goal of developing synchronized timetables at the network level while considering the uncertainty in bus running time. So as you know, main input to any type of model is data. However, in stochastic models, having comprehensive data is crucial. Datasets display the stochasticity of the system. Without good data, we cannot predict and simulate future uncertainty, and the model will end up unreliable. So the more data we have, the more variables we can add to the model to formulate the future uncertainty more accurately. And the common data sets are AVL, APC, and AFC data. But in our model specifically, aside from the network features, we also have operation data. We only consider segment running time as random variables in our model, but we also need a very detailed data for the different types of demand to minimize their associated waiting times individually. So one common solution approach for stochastic mixed integer programming model is a sample average approximation, in which a sample of possible uncertain system settings is generated and denoted as the sets of scenario. Then in the objective function is the weighted average of system performance over all these scenarios, which the weights correspond to the occurrence probability. In our model, different scenarios are based on distribution of bus running times. We developed two stochastic model, one stage and two stage model. The main decision variable is the departure time of vehicles from their terminal and transfer node, which is published and fixed for all the scenarios. But in the two-stage model, we have another set of data, which is for each scenario separately, and they recommend extra holding time at the transfer node for a bus. These decision variables can help us to formulate the future possible benefits and cost of real-time strategies now at the planning stage. So we define slack time variables to incorporate the randomness of bus running time system. And in different scenarios, we will have different arrival and departure times. So for example, if the vehicle arrives early, after it has its scheduled dwell time, it needs to wait until the published timetable. So in this case, we have waiting time due to slack, the in-vehicle passengers that can be true passengers or the successfully transferred passengers. If the vehicle arrives late, so it will depart later than it's supposed to be. Here we have waiting time for local passengers who come to the bus stop based on the published timetables. In the two-stage model, we have holding times. So if a vehicle arrives early or late, but it's held after the published timetables, we have that extra holding time for that vehicle, which now also the local passengers are experiencing that waiting time. The last waiting time in our objective function is the waiting time due to transfer, which is the difference between the arrival time of passengers from feeder vehicle to their connecting bus stop and waiting for the connecting bus to arrive. So as an example, consider a small network with 3 nodes, 9 lines, and 8 transfer direction at each transfer node. And we also define 2 scenarios. In order to evaluate 2 models, we also formulated a deterministic transfer synchronization with the average running time, which is the common practice. Then we examine each model in these 2 scenarios separately, And as you can see, the total value of the objective function, which is the total value of different waiting times multiplied by their associated demand, is much less in the stochastic models, which shows the value of a stochastic solution. This value is also higher for the two-stage model. And this considerable saving is actually due to the optimal slack time determined by the model, which leads to less waiting times. And so it's a benefit for both passengers and agencies. As the conclusion, we have two key findings. The first one is that the worth of multi, or in our case, two-stage stochastic models to formulate uncertainty in transfer synchronization, which can help us to bridge planning and operation stages more efficiently when using the two-stage model. The second one is the benefit of scenario-based solution method, which help us to formulate random variables in our model with more details and get disaggregated results. But as I mentioned earlier, the main need is rich data sets to enable us to actually formulate these variables and formulate the stochasticity of the system. As future extension, it would be more realistic to also consider passenger demand uncertainty in our model, and also to consider other types of real-time transfer coordination, such as skip stop or short turning at the planning stage. But this future extension needs a huge data set to actually all these variables. Thank you all for listening, and sorry for the interruption before.
Thank you, Sarah. Now we can have all your talk perfectly. Thank you very much. So we have some time for Q&A. There's not that much on the platform, but there's some that have been answered already in the Q&A forms. So I'm going to grab some of these, and I'm going to ask a few others, and to use our time wisely. The first one was for Rattanaporn. What do you calculate in the process when you evaluate the difference between the before and the actual total travel time? You explain it there, and so, but probably now that we have some time, you can go ahead again and ask a little bit and explain a little bit more about that.
Yes, thank you so much for your question. And according to your question, you mentioned that before and after total travel time maybe means the previous study approach and our study approach, right? If so, I need to address you again that we do calculate and evaluate accessibility from both approach in the same network, so that we have the results from two study approach. Then we just easily compare by finding the difference between our approach minus with the previous study approach, and we can see how different it is by visualize it by color legend. Yes, and as the result, we know that our study approach can minimize the total time to more realistic. Yes.
Thank you, Rattanaporn. For Igor, I have some questions. One was regarding of the type of vehicles and if there are some trials of this type of technology. How many buses are you going to replace with these modular units? And in your analysis, and that's one of my questions, are you computing also the waiting time for passengers? But because if you have more vehicles, then the frequency goes higher and probably the waiting time for passengers.
Exactly. That's the highest benefit. So that's the highest benefit basically of this technology, because by sending less vehicles, we are increasing the frequency at the same time reducing the passenger delay. So that's what contributes to the user basically cost function, and to the operator cost function. It contributes the fact that we don't have drivers associated to them, and the cost of operation of these units, because the technology is newer and everything is more efficient compared to basically operating the conventional bus. And the number of units, we limit also the number of units combined. Basically, for instance, let's say the capacity of a single modular bus is 20. And then let's say the articulated bus has kind of a capacity of 120 people. So then we kind of limit 6 of these units can be combined, so that we kind of have the same size as the articulated bus.
And in terms of congestion, when you have an articulated bus compared to, I don't know, 4 units, how is the congestion at the network level computed? It's going to be similar?
So yes, because this is a macroscopic perspective, and we apply so-called MFD, so macroscopic fundamental diagram for multimodal networks. And basically, so we don't really differentiate whether the bus is, let's say, 4 units or 6 units. It has an effect when it stops. So basically, the bus is kind of like, most analyses assume that buses and cars drive at the same sort of like cruising speed. So the cruising speed of buses is sort of like the same as the one of traffic. And then what affects the traffic is the stopping behavior of buses.
Perfect. Thank you very much, Igor. And I have a question for Nurit. Well, there was a question in the chat regarding if you were considering congestion in the network, and I have another one on terms of the decision of the passengers. Passengers in your model are choosing routes based on expected travel time. What's the decision model behind the passengers? And how much would you expect to change if you go ahead and you look, I don't know, if you have a deadline, if you I need to arrive on time to work, and you don't care if you're on average, how long it's going to take. You're really worried about not arriving late. It's going to be a different setting, no? Would you accommodate in your model for something like that, or would it be very complicated? I don't know if you follow the...
Let me answer the first 2 points.
Yeah.
The third, I didn't completely understand.
Okay, go ahead.
But okay, so for the first 2, so yeah, I had a question about whether we consider capacity of the vehicle, of the buses. And in the comparison table I showed, so no, that was the first one without capacity constraints. Later on we did. Applied strict capacity constraints, and we also consider this kind of information, congestion state of the bus information, and then we compared cases that the passenger has it or not, and I wrote in the Q&A the reference for this paper. Second question. Yes, we assume the passenger use the predicted arrival time information. So I do believe it models this behavior, but of course it's not realistic, as not all passenger has this kind of information. So I believe to receive a realistic results, we should do the average of few models with different information levels. But in each, we assume perfect information.
Oh yeah, so you have perfect information when you're taking the decision. You don't change your route during along the route. You might not change your. Okay.
No, this is a frequency based, so we use the average ridership.
Okay. But when you have online information on top of that, you can see when it's the next bus coming. So that you're taking decisions at the stop on a frequency based. So you're okay. Yeah.
Exactly.
Thanks. Okay. Thank you very much. And for Leah, there's yeah, similar question for you, Leah. I wanted to be sure that you're considering a fixed route for passengers. Can they change along the route?
The prediction we do is route based, so
Okay.
It's like route by route. So we consider the passenger like later on when we implement the translation in the ESP.
Okay, so you fix the route, and for that fixed route, you compute the
yeah. Sorry, it's like the prediction is for a specific trip done by on a specific route. So maybe it's a bit confusing with the terms, but like the route would be just like the start at one terminal and then the end of this trip at the last terminal.
Perfect, thank you. Well, for Sarah, so you were using this idea of having sample average approximation for computing the, if your solution was feasible or not. That's what I gather from your presentation, no?
No, actually, like instead of using integrals to calculate the expected values, we use the sample average approximation method to define different possible scenarios that would happen based on those distribution to replace that objective function with the expected value of system performance over all these scenarios with their probability.
Ah, okay, so just it's only the expected value, the one that enters.
Yes.
Okay. Yeah. And in your computations of transfer on your small network, let me try to understand correctly. So you have how the trips are fixed?
The number of trips are fixed. Yeah, the frequency of each line is given as fixed, but we somehow shifted the vehicles to get good timetables. But in stochastic nature, we have a published timetable, which is a published one, and we cannot change it. But we come up with that timetables in order to work in all the scenarios with their probability of occurrence to get a minimized expected value. But because in different scenarios, different arrival and departure time happens, because we have different running times between the nodes. So when the vehicle arrives, it will be later or earlier than that published timetable that is fixed. So then we calculate different types of waiting time, and then we try to minimize all of those over all the scenarios.
And the distribution of travel time that you are, where are you sampling those for? Do you assume a distribution?
We don't use the distributions directly. Using those distribution, we generated these the scenarios that we use.
And how do you come out with those? Are they based on real data or just?
For this example that I showed, no, it's the fake data. Okay. We just use some normal distribution with different values and then generated some samples.
Okay, let me see if there's more questions here in the.
Can I ask a follow-up question for Zahra?
Go ahead, Alarissa.
Yeah, thanks. So I understand that single stage or the first stage of the problem. So you optimize the decision variable, the planning decision, for example, the schedule or the departure. But I wanted to know more about the second stage. If I understand correctly, this includes some recourse decisions in real time, for example, holding. I wanted to know what is the specification of the model and how the model is solved in real time to optimize those real-time decisions.
When we say two-stage stochastic models, that recourse decisions are not necessarily going to happen, but we consider that for different scenarios that, for example, if that scenario happened and if we have that opportunity to apply that extra holding time, we can get like less transfer waiting time, for example. But these recourse decisions are not something fixed. We are not publishing that. It's something that based on different scenarios, they will happen, but we are just considering their possible benefit and cost at the planning stage. But we know that because specifically we are considering scenarios, we are not sure that that specific scenario will happen in reality. So that recourse decision is not exactly going to happen, but we are considered that at the planning stage to just know that we have that option. Like in the two-stage models, for example, if you also consider another examples, the recourse decisions are not necessarily going to happen. It's just after the uncertainty revealed, we can decide for those recourse decisions. But now at the planning stage, we just consider their possible cost and benefit in our model. did I answer your question?
Yeah, thank you.
Okay.
Well, still, Alireza, I wanted to ask you a little bit more about the time frame for using a model like the one you're proposing. So you would like to use it to understand when is it happening, or go ahead and that you have previous information of an event like this? Because I assume it's very difficult to predict something that you don't have in your data, no?
Yeah, that's a great point, because of the short duration of the presentation, I missed the detection part of it. I'm happy to provide more information, but we used Mahalanobis distance. It's a statistical measure, and when we apply it to a time series of the data, for example, in this case, we had 1 month of the data. It can be more, several months, for example. It actually inflates or exaggerates the demand at those locations and during the time that the event happened. So instead of looking at the just ridership, we can look at those Mahalanobis distance and detect those events. That's the detection part. And sometimes we know about the events, for example, the Minnesota State Fair. Sometimes we don't know about the events, like local fairs, etc. And that method can be used for detection. I don't know if I answered your question. I think there was a second part to your question.
And the type of events will differentiate on the level of demand for public transport, or will also I don't know, it might have an impact on the travel times for buses. Sometimes you have some street closures and stuff like that that will alter your operations. Are those type of events also part of what you're looking for, or only demand?
Okay, that's a great point, because our method, so the principal component pursued can be a general method. It can be applied to travel time prediction or demand prediction for special events. But we did it just for the ridership of one route. We didn't look at the travel time, for example. But the key point is that we can detect and quantify the deviation from normal, but we cannot say necessarily this is because of this event. If we know about the event, yes, we can say most likely this extra demand is because of the event. But if two events are happening at the same time, for example, with this method, we cannot say how much of the extra demand is for event A versus event B. So that's one of the limitations of the study. Perfect. Or if there is any reduction in the demand, we can detect that. We cannot say necessarily why it's happening.
Yeah, of course. Thank you. Well, I think we're on time. I would like to thank all of the speakers, and we still have our last day on transit data, so stick around. We have a break right now, and then we should be back in the program at 10:20 for the next panel discussion. Okay, thank you very much.
Thank you very much.
Thank you.
Bye.
Thank you.
Thank you.